Hello everyone, my name is Rudra and our group is going to present on the paper titled Pruning via Merging, Compressing LLMs via Manifold Alignment Based Layer Merging. So, why do we need model compression? It's because in production we often to deploy our trained models on edge devices such as our mobile phones or SoCs. These devices have very low compute and we cannot directly run our models on them. Another point is to minimize the engineering cost. For example, running these complex models tend to use more maintenance are hard to scale for large user bases. For example, in the Netflix's price competition, the highest scoring model could not be actually deployed into production due to this exact reason. So this is why we need model compression. Now, why this paper's method is because even though there are compression techniques such as pruning and quantization, which we will explore later, they don't work very well with LLMs in this field when we are compressing at a very high compression ratio. And this paper utilizes the opportunity of compressing redundant representation in neighboring layers, which other methods did not do.
Thanks, Rudra. I am Soham, and I will be talking about the recent works. So, training LLMs is especially hard because we want to learn from high-dimensional data. So, we use manifold learning. So, this allows us to project data from higher dimensions to lower dimensions while preserving the structure. So, some common methods are PCA, TSNE, UMAP, and diffusion maps. Now, some common compression techniques that we use are pruning, quantization, and distillation. So, as Rudra mentioned, quantization and pruning. So, what quantization is basically using lower precision for weights. For example, we use 8-bit integers instead of 32-bit floating points, hence reducing our memory footprint. Pruning is removing the redundant weights or channels, and knowledge distillation is in which we have a pre-trained teacher model which we use to train a smaller student model. Now, the more recent approaches are model merging techniques, and the most basic one is model soup, where we have multiple fine-tuned models, and we just take the weighted average of these models to create a merged model. And there are more advanced and dynamic methods such as Della, checkpoint merging, and tandem space merging. So, how our approach differs. So, these compression methods often lose knowledge or performance, and model merging techniques requires multiple models, but they are constrained to have the same architecture. Hence, we are limited. And whereas our approach, that is MK, we align and merge knowledge across layers and not just the entire model. Hence, we can achieve a compression and high performance retention.
Thank you, Soham. Hello, my name is Aryan and I'll be discussing the actual MK algorithm. So what we do know is that we need to compress these LLMs and we need to merge layers. That is the main idea, that we need to merge layers, because the premise is or the assumption is that these layers actually have redundant information, or the information that they have in them is quite similar. Hence, we can reduce this information by merging two layers as one. Now, one key note before I go through the algorithm is that here the word layers is actually referring to one transformer block. So you can imagine that there is one transformer block and there is another transformer block, and we are actually talking about merging two transformer blocks which are referred to as layers. Instead of a single MLP, or instead of one of the attention matrices, we are talking about layers as transformers block. Let me go through the algorithm. So the first step is that we will use a data set, and we will pass it through one of the layers one after the another, and we will get all the activations for each of the individual layers. And we call these hi of superscript I. The next thing that we do for individual transformer blocks, given that we have the activations over a data set, we will build a manifold. A manifold is basically in which we will make a Gaussian matrix W, which basically talks about the uh, correlation between sample I and sample J. And similarly, across all the samples that we have passed in the given data for the given layer from a given data set, right? So we build an affinity matrix. Similarly, we build a degree matrix that is denoted by D, and this turns out to be the diffusion operator, right? We are making this into a diffusion operator so that we can do manifold learning, which I will come to in some time. Now, given that we have this already, the diffusion operator P can actually be written in a symmetric form. And because it is writable in a symmetric form, in that form, we can eigen decompose it and get the eigenvectors and the eigenvalues. Based on the eigenvectors and eigenvalues, in lower dimension, we can form embeddings or diffusion map that are psi superscript L that are denoted by that, which basically are some sort of uh, object or a structure or a curve in a lower dimension, which are able to represent a given layer and its weights based on a given data set. The step 3 that we do is that we have these psi for individual layers. So L is a layer and M is a layer, and we have these psis for every single layer. What we want to do is that we want to compare the embeddings of layer L and layer M. So hence we compute a mutual information between them, and we then normalize them for each of these comparisons, each of these LM comparisons, to get a similarity score S subscript LM. Now, here, what we do is, here we have a threshold that is empirically set, and whenever the threshold is above this similarity score that we have generated for two layers, we know that these two layers are worth merging. Another important note is we can only merge adjacent layers, right? If I have a layer 1, layer 2, layer 3, then layer 1 and 3 cannot be merged because they are not adjacent, and that would mean many other difficult architectural challenges that come our way. Similarly, we merge them on the basis of a simple weighted average in which we use an averaging factor of alpha, which actually is the similarity score in itself. And the last step is step 6, in which we do this iteratively, which means we do this for every single pair of layers in which we do get a similarity score above a threshold, and hence we feel that it is legible enough to merge them and reduce the size of the language model. The output is that we get a compressed model M star with fewer layers, and hence we are preserving performance. Finally, the same can be seen from an image from the paper, wherein we are first calculating the activations of multiple layers, then we are building the manifold for each of those layers, then we do similarity-based calculation for adjacent layers L and M. And once we have done, we calculate a fusion ratio, which in our case was alpha. And once we have calculated this alpha based on uh, a weighted average sum, we define new weights and we define that as a new layer. And in the last step, we do this for multiple such layers of the network.
Thanks, Aryan. Hello, myself Aditya. I'll quickly summarize the experimental setup. First, for datasets, the authors used a diverse set of 5 benchmarks, including MMLU, Pika, and HellaSwell, to evaluate everything from common sense reasoning to broad general knowledge. Next, to ensure the method was generalizable, they tested it on a range of popular LLMs, including Llama family and Mistral. And finally, to measure its performance, they compared MK against already established methods, baseline methods in pruning and quantization methods like short GPT and smooth count.
So now let us compare MKA with other structured tuning methods on the MMLU dataset. What happens is first, let's define a metric called the compression ratio, which we denote as CR. That is the difference of the total layers, L total, minus L retained by Q upon L total. Now, the meaning of this metric is that since you have the factor of 1 by Q, there is an account for quantization, and also you're taking into account the difference in the number of layers after you merge. So it takes both of these into account, both of the compression techniques, quantization and merging of layers. So that is how we define the compression ratio. And you can see in the figure that we have 5 different models, and we compare MKA with other structured tuning methods. You can see that the performance of MKA is quite similar to reverse tuning, And you can also observe that reverse pruning and MKA are the best performers among all the methods. Uh, One thing to note in particular is in the case of Mistral 7B, you can see that we actually have better performance using MKA and not using reverse pruning. So you can say that we can conclude from this that MKA is more robust because we have different architectures here and we have uh, very great results from MKA. And let's compare MKA with short GPT with quantization on the MMLU dataset. So what we can find is that models pruned with MKA can be further quantized and maintain performance with a higher compression ratio. So you can see we have comparisons for three different models: Llama 2, Llama 3, and Mistral. All of them are 7 to 8 billion parameters. You can see that we have vanilla models, we have short GPT with three types of quantizations, and also MKA with three types of quantizations. You can see that the compression ratio is we have very high compression ratios, right? We have using short GPT and MK, we're able to achieve the same compression ratio, but we're able to preserve a lot of the accuracy. You can see that in the case of Llama and Mistral, we're able to achieve very similar accuracies as compared to the vanilla model. So this is actually very efficient in terms of memory. And the conclusion of this, when we compare MK and short GPT on various benchmarks, is that merging as opposed to pruning retains better performance across multiple benchmarks. So in this model, again, you have some vanilla models, you have short GPT and you have MK, and you have different data sets. You have MMLU, Pika, HellaSwag, Research, etc., etc. So we have a fixed compression ratio, and we're able to see that MKA has very comparable accuracies compared to the vanilla model, while having a very high compression ratio.
Hi, I'm Laksh, and I'll be discussing the future work of this paper. In the paper, they have only explored large language models, and as a result, one of the direction of this work could be exploring other modalities such as vision transformers and multimodal models. Another future work could be adapting this technique of layer merging to newer architectures such as lecture of experts and hybrid models. Let us now come to the novelty extension. So what we plan to do is this, that is intra-layer merging. So in the paper, what they use is inter-layer merging. That is, they merge entire blocks. They merge entire blocks. So for example, two attention blocks or two encoder blocks. So what we propose is intra-layer merging. And first, let us discuss what multi-headed attention is. So, in multi-headed attention, we have several self-attention blocks, and each has its separate QKV projections. In group query attention, the queries are unique for each head, but the key and the value matrices are shared across different heads. And the benefit of this is reduced memory and faster input. So this is our proposal. And previously, they merged entire blocks. What we propose is we merge only the key and the value matrices within each block. And the merge matrix then can be used across different blocks. This will convert the multi-headed attention model into a group query, similar to a group query attention. It will make the inference faster, and it will also reduce the cache that is required, and the performance drop might be lesser, which we'll have to explore.
We are only merging two names. But if you want to merge 0, 4 years with many iterations, so why not we merge 0, 4 years together? So what we can do is similar to the paper, we can take the similarity of 3 to 4 layers and try to average them out. And if it is about some threshold, we will take the weighted average of those layers. But our hypothesis is it might not work. For example, layer 1 and layer 3 has plus 0.8 and minus 0.8. It has very much information, but when we add them at, we come up to 0. And it will not give us that much amount of information. So we have a proposal. We can use hierarchical clustering. So as Aryan Solanki described that we have empathy for each of the layers. We will apply hierarchical clustering on each of the layers and we will get which layers are similar. And the layer which are similar, we will merge them via trials. So I will explain trials via this diagram. We have three model 1, 2, and 3. First we will remove the random noises. So from first to second you can see all the random noises are removed which are under a threshold. and then we will try to get the dominant side. We do it via majority voting, and we can see in first, second, fourth, and fifth the dominant side is positive, while in the third layer it is negative. And we will remove the non-dominant sign. And now we have only vector with a high amplitude and dominant sign. We will simply take the average of all the remaining vectors. This is tried and tested method for merging different models and it has worked.
So our experimental plan begins with baseline reproduction. The goal here is to replicate the results from the original MK paper to create a solid benchmark. We will use the same five datasets and same models by implementing their manifold-based block merging method. Next. Then we will start with our novel contribution, which we call intralayer merging, as explained by Laksh earlier. We will apply this to those models which do not use GPA earlier. So the procedure involves using activation manifolds to find and merge the most similar K and V projections. The query matrices won't be changed. We also plan to explore both a one-shot and iterative merging approach. Next, for our evaluation design, we will measure the reduction in KV cache size and decoding speed up. We will experiment with different numbers of query groups and report on key matrices like accuracy drop versus the baseline, memory reduction, and especially the inference speed up at long context lengths. So to conclude our plan, our expected outcomes are this. So our ultimate success criteria is simple. Achieve a considerable KV cache size reduction while still having a better performance retention than the original paper's block merging technique. Thank you.